we'll get the basics here. Potential energy is just really simple. You probably remember this from day one. Maybe where you guys talked about potential energy in middle school, and it hasn't changed any. Potential energy is still the same. It can be a real simple definition of it is a stored up energy. So we got potential energy. A lot of time I refer to it as a stored up energy. Okay, a lot of times that's what it is, and it's another way you can do it. It's probably a better definition. It's energy due to position or composition. So you got something spring-loaded, it's got stored up energy because of its position. Okay, you got something at the top of the hill, or top of a cliff, or top of a building. It's got gravitational potential energy due to its position. Okay? Now composition is more what we're going to talk about. Composition is more what we're going to be dealing with. So composition is how it's composed. And those bonds that hold them together, it takes energy to take them apart. But when you reform bonds, you get energy out. So most of the time when we have a bond form, if we're not forcing it, if we're forcing a bond, that means it's going to be unstable and eventually it's going to not be bonded anymore. So if it's bonded and you try to take it apart, it takes energy to put in, and so you have to add energy. Okay. If you have a bond form, it wants to form that bond and you get energy out. So we got these two words that represent energy that you put in and energy that you get out. Okay? And we're going to get to those here in a second. So the other type of energy that we can put something into is this thing called kinetic energy. So kinetic energy is just what it says. Kinetics is motion. So it's energy in motion. So it's energy due to motion. That could be motion of molecules. It can be motions of bigger things. Okay, a lot of times we can calculate kinetic energy, and we can calculate kinetic energy if we know what the mass of it and its velocity, and so that's called 1/2 mv squared is kinetic energy. So how fast it's moving and how much it weighs, and that's going to give us an indication of the kinetic energy. Right? There's going to be two words we're going to talk about. One's temperature and one's heat. They're different. Okay? A lot of times it's hard to differentiate between temperature and heat.
Is this dealing with kinetic energy still?
Both of these would involve kinetic energy. I guess they're separate. So really we're switching gears. So, okay? Temperature has, we can measure what's called average kinetic energy by taking the temperature. There's a correlation there. It's directly related. So the higher the temperature, the higher the kinetic energy. Okay? And it could also be a stored up energy, depending upon how you're going to use something that's, so it can be a stored up energy. It could be a potential energy too. So temperature is when you look at temperature, is related to motions of particles. Okay, and so it's like its average kinetic energy is proportional to it. So when we look at the temperature, we're kind of looking at its average kinetic energy. Okay, now heat involves really a transfer of energy. So heat is a transfer of energy. So temperature is not a transfer of energy. Temperature is just saying, hey, let's look at that thermometer. Once we look at that thermometer, it gives us a gauge of a standard, Celsius, Kelvin, Fahrenheit, whatever we're using, of its motion, of the particles. How fast are they moving? And heat is a transfer of energy. Okay? And we'll just go ahead and expand upon that. Between two substances. Okay, and I'm running out of room. And so on this next slide, I'm going to extend this. So heat is a transfer of energy between two substances due to the differences in their temperature. Okay? I got a little demo. I don't think I showed you this, and it's really not that impressive of an example, but we'll look at it here in about 3 minutes or 3 or 4 minutes. Dealing with heat and temperature and kind of how we can differentiate between the two. Okay, any questions you have on that information? Okay, now we're going to get into this idea. We're going to call it the first. It's not. We're going to call it. It is called the first law of thermodynamics. Okay, so thermodynamics is these are laws and you can't break them. They're not broken. And no matter where you go in the universe, they're not broken. Okay? So, when you look at first law of thermodynamics, is energy in the universe is constant. Okay, so what does that mean? What do you think?
You can't lose or gain.
Yeah, the universe has all the energy it has, and it's a certain number, and that number is not going to get bigger or smaller.
It's like the law of conservation of energy because it can't be created or destroyed.
Right.
It just changes form.
And we have to look at stored up energy and kinetic energy. So we look at the whole universe, and we look at all the potential energy that's out there, and all the kinetic energy out there, and then we add that all up, and then that value doesn't ever change. We can have kinetic go to potential, we can have potential to kinetic. When we look at that whole picture, that value doesn't change. So that's called the first law of dynamics. Whatever energy is in the universe, it is set, it's not going to change. Okay, you say, well, what about the sun? The sun is, well, it's got stored up energy as hydrogen. And so then the hydrogen will fuse together to make helium, and that gives off the energy. So it is still a form of stored up energy, as in hydrogen. Once the hydrogen's all gone, and all that, there's a lot of hydrogen in which to take into account. Okay, let's talk about these words that are pretty important for you to understand how energy kind of goes. So we have these words. This one word's called the system. Okay, what's the system? Okay, that's whatever we're focusing our attention on is the system. It's a chemical reaction a lot of times. So a system is the part of the universe that we're going to be focusing our attention on. And we're focusing on just that part of the universe. And again, a lot of times it's a chemical reaction. Not all the time, but a lot of what we're going to look at are chemical reactions. That's going to be our system. The surroundings is anything outside the system. So it's everything else. These two make up the universe. System, surroundings. We look at the system, okay? The surroundings is everything else. It's very important that you understand the difference between the system and the surroundings, because it can help you be successful to understand the difference between endothermic process and exothermic process. An endothermic process, the system brings in energy. Does that make sense? So if it's endothermic, we're looking at a system. It's endothermic when the system brings in, or energy flows in. So energy flowing into a system is called endothermic. So energy is flowing into the system from the surroundings. That's what we call endothermic. Exothermic is when we have the opposite happen, where the system is sending out energy to the surroundings. Okay, so if you can understand the difference between the system and the surroundings, you can figure out what's endothermic and when it's exothermic. And this, students have, and I can see why, have a tough time understanding why something would be endothermic when you look at it and it doesn't seem like it should be endothermic or exothermic. Okay, so that's important that when we're looking at the system, here's the system, and then everything out here is the surroundings. You guys don't have to write this down. That if we have energy going in, that's called endothermic. So endothermic process is energy absorbed by the system. Okay? When we do exothermic, it's the opposite. It's energy released by the system. And again, the system is anything we're focusing our time and attention on. Okay? So we're going to come up with, here before you guys go today, we're going to come up with, look at some scenarios of that. All right. Here's our first. We're going to go back to temperature and heat. This is boiling water, or near boiling. Okay. I'm going to put this in here and get it acclimated to the temperature. Let's put her in there. Okay. So I'm going to ask you a question. The lower part of this pipette that's in the hot water, okay? How do the temperatures compare? The water in the pipette and the water in the beaker. What do you think? Are they different temperatures?
They're becoming the same.
Okay, let's say it's been in there long. It's been there long enough. It takes on the same temperature, right? So right now it's the same temperature. Okay. Now which one has more heat? The water in the beaker. Basically, which one can transfer more heat energy? The beaker or the pipette? Water in the pipette. What do you think? Beaker. Let me give a demo of that. Okay, Dawson, put your hand down. Okay, I take a drop or two. I'm going to transfer energy from the hot water to your hand. Can you feel the energy?
Oh, I sure can.
Okay. But it's not painful.
No. No.
Okay, now when will it quit transferring energy to your hand?
Equilibrium.
Once they reach the same temperature. Okay? You can. Now, I'm going to take this beaker and you put your hand out. And I'm going to pour this beaker of water on
Oh
your hand.
boy.
Right?
Yeah, Dawson. Oh no.
Nobody's ever volunteered to do this, but Dawson doesn't. Okay? And if I poured it on his hand, there would be a lot more transfer of heat energy,
There'd be a
right?
lot.
So his hand would eventually get the same temperature as the water, right?
Yes.
Or not the same temperature as the water, but there would be an equilibrium reached.
Yes.
And there would be a very high temperature in which that would be reached. And that's why the hand would burn. That's why the cells in the hand would burn, okay, and die. Okay, and that's why the nerves would be kind of exposed. Okay? So if you spill something hot on you, the more you spill, and more is in contact with that area, then there's more chance of it doing damage to the skin. But if it's a little bit, but they're the same temperature, right? So the motion in these particles are the same as in the beaker.
Yeah.
Okay. But the energy that can be transferred of this water versus that water, it's a lot more energy can be transferred at the same temperature. Okay. So that's a little bit of a difference between heat and temperature. Okay. Now heat is initially just a transfer of energy. Okay. So we're going to talk a lot about heat transfer. Endothermic meaning heat absorbed. Exothermic means heat released. Now that heat can be transferred into different forms as well. It can be transferred to be stored up. There's a lot of things it can be transferred into because energy is usually transferred in from one thing into another. So here's some scenarios. Okay? Freezing. Is that an endothermic or exothermic process? What do you think? So our system is water.
When something is freezing, is that what you're asking? Like,
Yep, when something's freezing. So we got water at 0 degrees Celsius. And we're eventually going to get it to go to ice at 0 degrees Celsius. So that's freezing. That's what will happen. Water will start out at 0 degrees Celsius, and eventually it becomes ice at 0 degrees Celsius before it starts to cool down. Okay? Do you get energy out of the system, Or is energy going into the system?
I think it's going out.
It's going out. So that's an exothermic process. You've got to take energy out of water to make it ice. Okay? So this would be exothermic. So this is kind of what happens in your refrigerator. Your refrigerator gets cold, right?
Mm-hmm.
Energy's taken out. How's the energy taken out? Somebody know?
Isn't there a thing,
There's
a
a
vent
vent.
at the
There's a-
top?
No, there's no vent. There's no vent.
I thought there was too.
No.
Because it's always super warm.
Now,
when you touch the
refrigerators have a compressor.
Oh.
So what happens? You got a refrigerator. It's got a motor, and the compressor goes out. You're in trouble
Oh.
because it compresses Freon. So then we got this line that's full of liquid or gas, depending upon so this gas called Freon will be compressed into a liquid. Yep. So when it comes out, it's a liquid, and then that liquid will warm up. And by the time it's down here, once it passes by the part of the refrigerator or the freezer that is cooling down, it will go into a gas. I hope I have this right. Now, to go from a liquid to a gas, is that endothermic or exothermic?
Endo.
Okay, so that's endothermic. Where does the energy come from to do that?
In a refrigerator?
Yep. Where does the energy come from to change that liquid to a gas?
Outside?
Nope. So we got a refrigerator with all our goodies in there. Okay?
Is it coming from energy given off when it cools down?
So there's air in there,
Yeah.
right? And it's moving around. And so guess what? That air is going to warm up the liquid, change it to a gas. So what do you know about the air molecules when it gives up its energy? What's the motion going to be like once it gives up its energy? Going to be moving slower. And depending on how slow you want it to move, you can get it to be like a freezer or the refrigerator compartment. You got things on there. So if your compressor's running all the time, you probably have it set on a cold setting. Or it's hot in the room. Okay? Does that make sense? The liquid goes to the gas. It's endothermic. The energy has to come from somewhere. It comes from the air and also the food, right? Because when you put food in there, it's at room temperature. And now it's warmer than this liquid. And guess what happens? It gets it. Now, it turns into a gas. It comes back to the compressor. The compressor runs, takes electrical energy, and compresses that gas into a liquid again. Then it runs back through, compresses, runs back through, compresses. So you're using electricity, which is another type of energy. And that's how, and that's also how like an air conditioner works too, same way. It pushes air by these coils. And so where does the energy come from to change that liquid to a gas? From the air that goes by the coils. And as it comes by the coils, now it's cooler. And now it cools your house. But when you look at your electrical bill, and it's $300 and something because it's 100 degrees outside, then that's paying an electric bill, some money. So it's kind of neat that you can see something that is something we use every single day, and it's just changing a liquid to a gas. Now, if you get a hole in this line, you're done too. you gotta get a new refrigerator. Compressor goes bad. It's tough to put these new lines on because they have to be sealed so good, and it's once the compressor goes or whatever, you're done. So like I have apartments and I got like an air conditioner. When the air compressor goes bad, it's like, oh, good. Now I got to pay $3,000 or whatever to put a new one in, type of thing. And then they got to run in new coils all the way through up to your unit that's sending the cold air through. So there's a couple instances for that. I'm going to give you an assignment. It's not that big of an assignment. It's not going to take you a whole lot of time to do. Your assignment is going to be where you're going to be making these determinations if it's endothermic or exothermic. Okay, and it's kind of like the liquid and the gas type of thing when you're doing it. Okay, so let me find ones you're going to have to do. Well, why don't we wait till tomorrow? And then we'll do it tomorrow right away. Okay?